Hello, everyone. So I'm going to talk about our improved analysis, gap dependency analysis of the noisy power method. This is joint work with Professor Balcan, Yining Wang, and Adam Svei. We are from Carnegie Mellon University. So we consider to compute the single value decomposition, where we have an input matrix A. We assume it's positive semi-definite. So this is just for the ease of notation. So the single value decomposition of A is just, we can write it as one orthonormal matrix multiplied by a diagonal matrix and then the transpose of that orthonormal matrix. And the single values are just decreasing D single values. And if we want to find the best rank K approximation, it's just a UK sigma K and UK transpose, which minimize the Fermi's norm and the spectral norm. So we consider to compute the first K eigen or singular vectors. So our output is not just a dimension K matrix, it's a dimension P matrix here. So we have some redundancy. And our measure is angle between these two linear spaces. And our goal is to minimize that. So power method is a traditional method to output this matrix X. So you just left multiply the original input matrix L times, and at last you just renormalize it and output the orthonormal matrix. So for noisy power method, it's a recent work by Maurice Hart and Eric Price in 2014. So at each iteration, we have an additional noise here. So this noise can be possibly adversarial. And so at each iteration, we left multiply the original matrix by original matrix. And also, we renormalize it to stabilize the procedure. So it has many applications, such as if this noise matrix is Gaussian noise, then we can obtain a differentially private PC. And if, just as the last speaker said, we can use power method to compute the streaming PC. So in their paper, they have this theorem. So if the noise strength is on the order of epsilon sigma k minus sigma k plus 1, so this is a consecutive spectral gap. Also, if you project the noise matrix onto the first K eigen vector space, the noise strength should be at most in this order. So this term is from the Gaussian initialization. So after enough iterations, we can say that the angle between these two spaces are small. However, since we have so the output matrix X, so this is our result. So if we have the output matrix X is a D by P matrix, so we expect that we can enlarge this spectral gap in the convergence. So this is our result. We enlarge this noise tolerance in terms of the spectral gap. So Q is some intermediate term which is larger than K and smaller than P. So in that, this spectral gap is enlarged by some order, and if suppose Q is 2K, if we assume the matrix has a polynomial decay, we can have an order K improvement. So our result can directly lead to improved bond in the streaming PC and differentially private PC. So our main technical contribution is that we define a new term for the to characterize how close to linear space are. So originally, many matrix analysis relies on the shrinkage of the tangent between two linear subspace. This is used in Maurice Hart analysis. But here we consider a new term. So we consider the UQ, which is a larger eigenspace, and so at the right, we multiply by an identity k by k matrix. So intuitively, this is a noiseless case. We can write an iterative inequality. So after multiply by this k by k identity matrix, we can extract the first k eigen values. So we can have the convergence rate become like faster. So if we do not like multiply by this identity matrix, then here will be sigma q plus 1 or sigma q. So it's a smaller convergence rate. So we should note that Professor Minggu from University of California already used implicitly use this kind of measure to prove the noiseless power method. So also based on our larger spectral gap analysis, we can directly have gap independent bound in terms of the spectral norm, and just using a simple trick from Scott's paper. So the epsilon dependency is squared. We assume that it can be improved to like epsilon here. So in conclusion, we define a new measure of for the two linear subspace, and we have improved the spectral gap dependency for the noisy power method, and we propose a gap independent bound in terms of spectral norm. So some open problems, how probably we can improve the epsilon dependency. Also, it's possible to have some analysis for the noisy block-Lanchas method. Okay, that's it. So the question is what the intuition behind the potential function, like it's this, right? So I don't have a very geometric like intuition, but the main intuition is just this inequality. So we can have because we multiply by the k by k matrix, we can have a better convergence rate. It's like a numerical trick.